lecture, we had this example where we tried to design a column. And I know that the column discussion looked like scary, very, those kind of interaction diagram. I know they are scary and intimidating. And some of you, they say, no, that's very difficult. And I said interaction diagrams, they look intimidating and difficult, just like me, but they are easy. Okay. So we had an example by numbers, and that was this where we stopped the last class. And I have another example today. So if you haven't followed last class, or if you haven't attended last class, or if you haven't watched even the video last class, then there is a chance for you to, understand how do we design a column. The last part that I haven't really finished is the splice length. So on the screen here, what happens is when we build the column, so I'm referring to this column here, simply the rebar or the vertical bars doesn't just stop here. It has to keep going and projected above the top of the slab by certain amount where it overlaps with the next cage or lifts. Okay, and so we need to make sure that there is enough length or overlap between the rebar. This overlap, we call it splice, and it depends on several factors, and I'm going to discuss on the next slide. Now, why do we need splice? Simply because we don't weld the rebar. So we don't really weld the rebar because welding the rebar is very expensive, and even the material of the rebar is not weldable, so you cannot weld. And so the way we transfer the load from one bar to the next bar, remember the load path is coming from here. This is the load path. So there is forces going here. And then we need to safely transfer the load into the next rebar. Okay. How we do that? We do that through the bond. So the concrete is simply like wrapping around those bars, and the concrete will simply transfer the load gradually from this bar into the bar going to the column below. Now, when you think about this process, you will see, I'm going to explain for you the factors, and it could be one of the theoretical question on the final exam. Okay, so the factors that controls the length of the splice or the overlap length is simply it depends on the strength of the concrete. Okay, I want you to don't really try to understand the whole table, but for now, I want you to understand and look at the table and get this idea. When the concrete is weaker, we need a longer length. For example, take this example. Let's focus for the column that has 15 m. So this column here, it's column for 15 m. And watch what's happening, huh? If my concrete is 50 MPa, then I need 310, which is roughly 12 inches. The weaker the concrete, so on this end here, concrete is 20 MPa, and with 20 MPa, I need 480. It means when concrete is weaker, I need more overlap. Does it make sense? Need to hear some noise, please.
Yeah, that makes sense.
Okay, what's the other factor? Number two is the bar diameter. The bar diameter. So when the bar gets larger, then we need a more overlap. Watch this, please. So I'm going to take only one example. Let's say 25 MPa. So if you have a 25 MPa and for 15 m, I need 430 mil. And if I increase my diameter going this way, guess what? If I have 35 m, then I need like 1260 millimeter. So that's 1.26 meter. Okay, so you can tell the other factor that controls the length or the splice length is the diameter of the bar. The larger the diameter, we need a more splice length. Now, the last factor that controls the splice length is it tension or compression? Is it tension or compression? Can anybody help me and just guess, get like a, try to guess. if I have some bars and they are in tension and some other bar they are in compression, and remember everything else is constant, which means same concrete strength, same bar diameter, but the first group is in tension and the other group is in compression. Which one you think requires more splice, the tension or the compression?
Should be the compression.
So the compression requires more overlap to transfer the load from one bar to another bar.
Yeah.
Okay, so sorry to tell you that this is not really the right answer. The right answer is concrete is kind of weaker in tension. It needs more splice length if your bar in tension more than it is in compression. Now, how do we know? And some of you may think, oh no, Tahir, stop. Listen, stop. Columns, they have a compressive force, and so which means all my rebar will be in compression. Do you agree on this statement? Like columns, they have a gravity load, they are in compression, which means all the rebar in my column will be under compression. Would you agree? Can this be a general statement or
Yes,
no, it cannot?
Yeah. Yes, it is.
Okay, so the answer is no. What I said is not true, and I will try to convince you. Okay, so here is a side view of your columns. Here is a column. Okay, yes, of course, if my column is centric column, then if it's centric column, which means my load is acting at the centroid, then the stress over the entire cross section is compression, which means all the rebar, whether or on this side or on this side here, both of them, they will be in compression. Okay, so those bars, all of them, they are in compression. Let me ask you, what if this is the case? What if I have a bending moment acting on your column? Bending moment acting on your column. I don't know how to add here like a head. Anyway, get the idea here. I'm trying to draw here a bending moment, So if I have a bending moment, do you think the stress diagram will be the same as constant? Like, not sure if you're following, like this will be the stress
No,
diagram.
it
This will
wouldn't.
be the stress diagram if the load is in the center. If we add bending moment, let me ask you, the stress diagram will stay the same as constant stress all over the cross section, or no?
No.
Okay, so yes, no. So it could be this. It could be more compression on this side, and it could be less compression on this side. So more compression on one side and less compression on the other side. So that's one option. Or the other option is simply it could be like so. It could be compression on one side like so, and it could be a tension on the other side. So this is you have here compression, here tension. Now, why do we sometimes get this diagram and sometimes we get this diagram? Can anybody tell me it depends on what?
Is it eccentricity?
It depends on the eccentricity, correct. If the axial force is within the middle third of your section, it means you don't see any tension. One side will be more compression and the other side will be less compression. If this axial force goes off the middle third of your section, then in this case, what happens at exactly at the 1/3, you'll get zero. At 1/3, one side will be zero stress and the other side will be compression. If you go outside the middle third, then one side will be compression and the other side will be tension. And what happened here is, as Muhammad said, it depends on the eccentricity, and I would say it depends on the moment, huh? So let me give you some math here, okay? So E, let's say E is equal to eccentricity, Okay, so E is the eccentricity. Okay, and P is the axial load, and M is the moment. Is there any relationship between the moment and eccentricity and the axial load? The relation is here. So the moment is equal to P, which is the axial load, multiplied by the eccentricity. And you can tell the more eccentricity we get, we get more moment. So it depends on the eccentricity. And so how do we know? You can tell if you look at the table right now, one more time, you will see the table is simply chopped into 3 zones. Here is your first zone. So this is zone number 1. And in zone number 1, it says compression only. Compression only, it means there is only, the entire section is in compression. Entire section is in compression, which means your force is still within 1/3 of your section. Then the zone number 2 in your table, which is here. So this is zone number 2 here. It says class A, which is tension splice, which means the Fs over F field is anywhere between 0 to 0.5. And those are the length. You do that if it's case number A. Please be patient until I show you what is case A and how do we know if it's case A or case B. Finally, this is the last part of your table, which is called class B. Class B, which is anything else that's not class A or compression only. Now, here is the point. We said before that if yeah, like this one here is axial, pure axial force or centric force with a little bit of eccentricity, which turns your entire section into compression only. This one here is like a beam, which means one side is in compression and the other side is in pure tension, which means the stress in your rebar will become F field. How about this one here? This one here is something in between. Now, how would I know? Of course, if you know it's compression only or class A or class B, right away, you know where to go in the table to find the splice length. Now, let me show you where or how to find your class A or class B. Here is the secret. The secret is between 0 to 0.5, because those numbers will help us on the interaction diagram. Let me go to the interaction diagram. So here is interaction diagram. And what did we use interaction diagram for? Simply to find the rho, the reinforcement ratio. I'll show you another use of the interaction diagram. So you can tell here, so in the interaction diagram, this point here on any interaction diagram, it means centric load, because you can tell on this one here, like the y is equal to number, which is P over A is equal to number, while the M is equal to 0. So it means I'm subject to my column to pure axial force. Pure axial force, centric, no eccentricity at this point. And as we go along the curve, any curve, doesn't matter, the eccentricity is increasing, is keep increasing along the curve. So all these points, it has more eccentricity, but still, all the section is in compression. The first point that you will start seeing some tension on one side of your concrete is this point here, which is Fs over E field is equal to 0. From this point on, the force will go outside your middle third, and then all these points, we have some tension, but it's not really F field. The ratio between the stress in the steel to the F field is anywhere between 0 to 0.5. How about here from these points, like all these points here, this one here, the Fs, the stress in the steel is equal to the F field, because this works like a beam with the mainly moment without any axial force. So really, how do we answer this question? Are we compression only? Are we case A or class A or class B? Very, very simple, although the discussion may look annoying for you. Okay? So very simple. All you have to do is remember that we plot here one point. Remember this point here that we plot to find how much area of steel we need based on P over A and then M over A times H. Only the ones that follow my advice and read the lecture notes before the class today will know what I'm talking about. If you never listen to my advice, for sure, you don't know anything I'm talking about right now. This point here is how do we find the reinforcement ratio? By estimating this number here, which is M, whatever moment applied to my section, divided by A times H, and this number here is P divided by area gross. We get a point here. This point will tell us whether it's class A or class B or compression only. What happened is here, this zone here, and I don't know how to draw this. I want to draw, so this zone, which is between this line, I'll try to do my best. Please forgive me if I can't. But this, I'm gonna make it thick. So this zone here, it's simply, this zone is the compression only. All this zone is compression. I think when I make the lines thicker, you will start to see what I mean. All this zone is compression. Okay, so this zone here where my cursor is, it's zone, it's compression only. How about splice A? Okay, in the table it says between 0 to 0.5. So let me try to do it one more time. I'm gonna change my color to, let's say, to blue, and then draw a few lines. Okay, so here is my line here. It's very annoying. It's just changed the color by itself. So here is one line on splice A. It's anywhere between Fs divided by F field from 0 to 0.5. Probably I need to make the lines are thicker so you guys can see. So anywhere here, this is simply Fs between 0, Fs divided by F field between 0 to 0.5, and this area here is splice A. So very simple. Look at my lines. So this was the point that I did my design, and if you extend the lines, you will see it is between Fs divided by F field from 0 to 0.5, and that's why my column must have a splice A length. What happens if my point, like let's say you estimate the two numbers and you get 1 point here, okay, 1 point here. I'm asking you, what kind of splice length do we need? Do we need compression only, or splice A or splice B?
Splice B.
Splice B. And so all you have to do is very simple. The discussion, I know it looks annoying and very difficult, but at the end, what you have to do, once you locate the point in the interaction diagram, you just have to see, depending on where is the point. The point in this zone, it means compression only. From 0 to 0.5 is splice A. Anything after this one is simply, it is a splice B. And so now let's go. We know this splice A. So because we know it's splice A, now we can tell we are in this part of the table. So 40 MPa with 20, so we need 460 millimeter. Really what's important for me also is to understand what are the three factors that controls the length of the splice. Number one is the bar diameter. Number two is the F prime C. And number three, what is the stress in the rebar? Is it compressive stresses or tension stresses, but a little bit, not much, or very much like a beam, so your rebar is yielding? Okay. And so any questions so far?
No, not so far.
Okay, so I'm gonna right away, just for sake of time, I'm going to go to my other presentation, which is available right now on the D2L please ensure you download the design 2 and also the first one, because what I did, I know that there was some mistakes, some errors that I found in the last few lectures, and I corrected them, and the new version is uploaded to the D2L. So ensure that you download the latest version. It is available together with the new presentation that I'm going to go through right now. So here is another example, and really the difference is, you will see, looks like it's almost the same problem. The difference is we're trying to design a rectangular column. In the last example, I designed a square column. In this example here, I will design a rectangular column, which you will see almost same procedure with a little bit of difference. Now, few input here. Number one is the axial load. So the axial load is 4,000 kilonewton, 4,000 kilonewton. And in this example here, I did not give you the moment explicitly, rather than to give you the eccentricity. And I think we discussed, we can find the moment by multiplying the eccentricity multiplied by the axial force, and that will give you the moment. Okay? And just to be clear, eccentricity, it can be either on the strong axis or it can be on the weaker axis. The eccentricity, if you guys remember, I'm gonna probably remind you right now. So let's say that's the cross section of your column, okay? And so the cross section, we have here the cross section, it has two axes, okay? So maybe my force is acting here, okay? And if the force is acting here, it means this is my eccentricity, okay? That's E. And if my force is acting here, okay, where is my eccentricity? My eccentricity, I'll zoom in. So my eccentricity will be from this point to this point here. So the eccentricity can be along the X direction, or it can be along the Y direction. So here in this example, I made it along the strong axis. The strong axis is the longest, 200 mil. One more thing, when you design a square column, is easy because simply the two dimensions are the same. If you design a rectangular column, we need to have one dimension of them is known. And typically this is given by the architect, because those columns, most of the cases, will be integrated into the wall, and they must match the wall thickness to hide them into the wall. Okay, so I used here 300 mil. So this number is given to you. Do not ignore this number if this number is given to you in the exam, okay? Because some of you, I say in the exam, design rectangular column, but nobody like listening, and they go ahead and they do square column, okay? Rectangular, it means not square. And for sure, if it's rectangle, it means I have to give you one dimension. The unsupported length is 3,000 millimeter. Concrete compressive strength is 400. We're using 20 M for vertical bars. We have cover of 40. And then finally, the M1 over M2 is equal to plus 0.5. It means a single curvature. Now, are you ready to proceed? As I said, we have an example in the last class. If you haven't watched it or you haven't attended, still we have time. Starting now. Okay, now I'm going to start and show you what are the steps to design a column. Number one, you need to estimate the approximate size of your column. The approximate size, how can we do that? We use a design aid. So the design aid needs only one thing from you, which is what is your axial force. So the axial force here is 4,000. The only thing is the chart needs the force in meganewton. And that's why a 4,000 kilonewton is 4 meganewton. Okay? Remember, we have so many of them. And that's why, please be careful. You must pick the one that corresponds to your F field and F prime C. So here we go. I have chosen this one. You can tell from my screen on the top left corner it says MBA 30, and for the steel is 400. It means this one here. Okay. Now when you look at the chart, and I've done this last class, we'll do it one more time. The chart is very simple. On the vertical side or the vertical axis, you need to enter with your PF, 4 meganewton. And then on the horizontal, it's your reinforcement ratio. Reinforcement ratio. We discussed in our class that the minimum reinforcement ratio for column is 1%. 1%. So we always start from 1%. 1%. And if it happens after I'm proceeding on my design and the column dimension gets crazy, what I do is I can go back and I change my 1% into 2% or 3% and maximum 4% to shrink or to be able to shrink my concrete dimension. That's it. But in most cases, 1% will work. Again, if you have a very, very heavy load and you are at the basement of a high-rise building, maybe you will face this when you need more reinforcement to reduce your concrete dimension. Now, I give you here kind of tips of what you do. So what I did, you can tell here, I'm going to zoom in, you guys can see. So I went with 4 meganewton and 1%, and I got 1 point here. This point, it happens in between 2 lines. So 550 by 550, and then the area gross is equal to 0.3025. Okay, so I said I make it easy for you. You don't have to interpolate. I'm trying to make your life easy. Don't interpolate and straight use this one, the higher one. So we have 550 by 550, and the area gross is 0.3025. Now, if your column is a square, here we go. If your column is a square, then your column is 550 by 550. How about if your column is rectangular, like our case? Very, very simple. Your P, the length of your column, is simply the area divided by the width given to you. Remember, the given to you is in millimeter, while here the area is in meter square. And it's very simple, huh? So the 300 mil, it is 0.3 meter. And what happened is here is I got the B, or the length of your column, is equal to 1 meter. Luckily, we got 1 meter, but just in case if you get any other number, not nice number, make sure you round up your dimension to the nearest 50 millimeter. Any questions so far? Please say yes or no so I can continue.
Not so far.
Okay, excellent. So now next, what you have to do before you do anything, make sure that the concrete column dimension meets the requirement for a short column. Because if it's not short column, it means we need to add a more moment due to buckling. And that's what we'll do right now. I will ensure here in this step that my column is a short column based on all the geometry available. Not very difficult. Look at this, please. So what you have to do is you estimate the KL. So this number is given, the KL over U, which is K multiplied by L unsupported, 3000. Next is you divide by the radius of gyration of your column. Now I know some of you will say, why, Tahir, you did not divide by the 1000? Why did you not divide by 1000? Any help? The column is 300 by 1000, huh? So why, Tahir, it shows the smaller dimension of the column?
Is the smaller dimension the weaker one?
Exactly, sir. Yeah, I chose the weaker dimension, the smaller dimension, because that's the weak. So the buckling always happens on the lambda maximum. So I'm gonna get here lambda maximum. You are able to get the other lambda for sure, the lambda about the y or x or whatever, but it will not be the maximum. Huh? The column will buckle around lambda maximum around the cylinder axis. Okay. So I got here 33.3, and so this is my my actual cylinders ratio for the column. Let's get the maximum. The maximum is the limit, not very difficult. Look at the equation. We go ahead and say 25 minus 10 multiplied by M1 divided by M2 and so on and so forth. I got from this, I got 30. Now, if the maximum is 30 and for the column is 33.3, what happened is this column, the way it is right now, based on the given geometry, like the column dimension and the length of the column, it is a cylinder column, not a short column. And that's why if we want to continue and insist on this dimension, there is no other way. You need to find the buckling moment, add the buckling moment to the moment from the loads, and we should design my column for the buckling as well. We cannot ignore it. However, if I do some magic, which is not really magic, I'll do something to enforce this condition to happen, then I'm going to enforce my column to be a short column, then I don't have to worry about buckling at all, okay? So that's what's happening in the next slide here. So without wasting your time, I tried to bump up the dimension by 50, and remember, the 300 is constant, and I will not, and take a note please, because this annoys me in the exam. Some of you, I give 300, and when they change dimension, they go ahead and change the 300 to 350 and 400. Do not change 300. You just have to change the other dimension, because as I said, why 300? Because the architect wants to integrate the column into the wall, okay? So I checked 300 by 1050 and so on. I kept increasing step by step 50 millimeter until it works only for 300 by 1250. Okay, let me show you. So on the check, you can tell the lambda still the same, doesn't change. Can anybody tell me why? Although I'm changing my 1000 to 1050 and so on, why the lambda stays the same? Muhammad said it a minute ago. I'm keep changing the length of your column, but the width is still the same, and the buckling will happen on the weak axis. So the lambda maximum is still the same. The other lambda in the other direction, yes, it changes, because I'm keep increasing the concrete dimension on the other dimension. So the other lambda definitely change, but the other lambda doesn't govern. This one, it what governs, which is the maximum. And I can make it clear here in red. I said buckling always happens on the weak axis. Now, all you have to do is go and find the other number, which is your limit. So I put here, you can see the numbers are the same. The only difference is your 1250 or the denominator over there, and we have 33.5. Finally, the 33.3, which is the lambda of your column, is less than lambda maximum, which is 33.5. Now and only now, my column is a short column, which means I can proceed with neglecting the buckling effect. Are you following?
Yeah, we're following.
Okay, so you guys know, once you know that your column is a short column, then we can start getting into our interaction diagram, because I know my moment is not going to change. My moment is only the one from the loads. However, the interaction diagram needs some parameters before you do that. And those parameters are simply which interaction diagram, because we've seen last class, we have so many of them, total of 76 interaction diagram. And we know why. Some of them, they are designed for different F prime C. Some of them, they are designed for different gamma. Some of them, they are designed for different rebar layout. And some of them, even they are designed for different shape, like a square or circular. That's why we have to get some parameters before we pick one of the interaction diagrams. Now, one of the parameters is your gamma, and not very difficult. You know the value of the gamma is simply the ratio between H prime to H on this picture here. H prime to H is your gamma. You can do that manually, or even faster, you can do it from the table. So from the table, you can tell my column dimension is 1250. My rebar is 20M as per my original problem. So you can see here my gamma is equal to 0.9. Very, very simple in 1 second. Next is, let's always assume that the rebar will be on all sides, Now, once you know, and remember the F prime C is 30 MPa. Now, once you know that, I went through all the interaction diagrams, and this one here is the one that I chose. Why? I'm going to show it, and then I'm going to go back. Look at the interaction diagram 7.10.8. The gamma is equal to 0.9. The F prime C is 30. The rebar is all around, and it's a square or rectangle, which means this is the one I'm going to use. Let's go back. Now, what do I need to prepare before I enter this interaction diagram. So I know now which one. But what do I need to prepare before entering interaction diagram? We need to find two numbers. Those are the x and y, the pair of coordinates that will locate one point on the interaction diagram. Very simple. You divide your PF, the axial load, divide by area gross. Not super science. Look at this, very simple. We have 10.7. Now, for the moment, I said this time different from the previous example. I did not give you the moment straight. I gave you the eccentricity, which is 200 mil. If you want to find the moment, you multiply the eccentricity, multiply by the BF, then you get the moment. Then you take the moment, you divide by the area gross. So this term here is the area gross, and then multiplied by the H. I know, I think Diego asked me last time. You asked me, Diego, which dimension is the H? Is it the small or the large dimension of your column? Here is the answer. It is where the moment is acting. Always the H is the dimension of the column in which the moment is acting. And if you remember, I said the eccentricity is happening on the strong axis or the longer axis. Let me show you. So here is your column, and the line. This is the center or the centroid of your column. The centroid of your column, and so the axial force is acting here, and this dimension is from here to there. This dimension is 200 mil. This is the eccentricity. So your moment will be around along the strong axis, and that's why where is my H? My H will be from here to there, which is this will be my H equal to 1250. How about if the moment is acting on the weak axis? In this case, your H will be the 300. In general, typically the moment we rotate our column, it doesn't make sense that our column, I'm gonna change the orientation so it resists the moment on the weak axis. We always change the orientation of the column so it will be on the strong axis. Okay, is that clear? So the H is not the smaller or the longest dimension of your column. It is parallel to your moment application. Remember, my moment in this case is acting on the strong axis. Now, as I said, very simple. You find this number and you find this number, and those two numbers are the ones that you're using in your interaction diagram. Let's do it. Okay, so I went here with 10.7 and then 1.7, and this created for me a point in the interaction diagram. Okay, a point in the interaction diagram. And as you know, any point within this first curve, it means rho is less than 1%. Any point within your first curve, it means rho is less than 1%. But we know that the code asks for minimum 1%. So what do? Is we know it's 1% because we cannot go less than the minimum by the code. So that's all I did. That's what you want. So here is the 1% coming from the interaction diagram. You multiply the rho multiplied by the width of the column by the length of the column, so you get area of steel. I think we need to break lots of information, so I'm going to break for 10 minutes, and we'll see after we come back. By now, does anyone have any question?
I don't have any questions.
Okay, so I'll stop the recording and I'll see you in 10 minutes. We'll see you back here at 2:03.